This is the video on Newton's second law. So remember, there are codes in the video. There are two codes. There'll be a written code, one that'll show up on the screen. The other code will be a verbal code said by myself. Each code will be 3 numbers long, and you will need them to move on with any homework assignment. So remember, when you're looking at these slides or watching this video, what's written in green is what's important, and you can make a nice notebook just writing what's in green. So this is the written code. I would recommend you write this down somewhere. All right, so the original question is, what is the relationship between acceleration, net force, and mass? And that brings us to Newton's second law, and it's known as the real law of motion. So basically, it states the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the objects. But Newton's second law is usually just written down as that equation, right? So this is the equation. Acceleration equals the ratio of net force to mass. So in Newton's first law of motion, he stated that net forces cause acceleration, that unbalanced force causes acceleration. When Newton's second law of motion, Newton quantifies how much acceleration is produced with any given net force. Now, Newton's second law of motion is known as the real law of motion because acceleration is the only real motion, and his second law quantified it. So he's saying that constant velocity and rest are the same thing. Acceleration is the only real motion. Now, basically what Newton's second law states is the amount of acceleration produced depends upon the ratio of net force to mass. And I've capitalized ratio because that's very important. It's the ratio of net force to mass. So I'm sure everyone has experienced this at some point, right? So when you're pushing the shopping cart, right, these are some questions. Which cart resists change in motion more? Which cart has more inertia? Which cart has more mass? These are the same questions. These are the same questions because inertia is resistance to change in motion, and we measure inertia with mass. Now, which card has a larger acceleration and which card has a larger ratio of net force to mass? Those are the same questions as well, because you can see, according to Newton's second law, that equation, the ratio of net force to mass is the same. So if you come in here and we look at that, well, just think about pushing that empty shopping cart, right? Very small mass, you push it with a force, and it's going to accelerate. It's going to accelerate with this ratio of net force to mass. That's a large acceleration because it's a large ratio of net force to mass. Now, let's just say I've got a full shopping cart. Now I've got a large mass. Now I'm still going to push it with about the same force, but now my ratio is a lot smaller. It's going to accelerate a lot slower. And you know that if you're in the store and you are pushing, well, it's going to accelerate a lot slower than if it were empty. Why do objects fall at the same rate in a vacuum? All right, so we can also answer that with Newton's second law of motion. So all objects falling have the same ratio of net force to mass. So think about it this way, right? If I've got a tennis ball, I've got a small mass, but I've also got a small weight. So we're ignoring air resistance, right? And weight is the only force that's acting on it. That'll be the net force. And this is my ratio of net force to mass. That's my acceleration. Now, if I look at a large like medicine ball, now I've got a large resistance to change in motion, a large inertia, large mass, but I've also got a very large weight pulling down on it, very large force. So I've got a larger force, but I've also got a larger resistance to that change in force. And notice this ratio, large net force, large mass. Well, I'm going to have a ratio, and that ratio is going to be the same for all objects. So, and in fact, we know that ratio. It's 9.8 meters per second squared, especially here on Earth. So first thing we did was we did the push-it simulation. You can see here, this one was just pushing a box across like a table. We were increasing the net force applied to it and the mass of that object. At this time, I'll go ahead and give you that verbal code. The verbal code is 824. I say that again, the verbal code is 824. Well, then we did this huff and puff lab. So this one is real easy. This one is just putting a golf ball and a table tennis ball on the table and like blowing on them, right? Blowing them across the table. And you'll see that that ping pong ball, that table tennis ball accelerates a lot more quickly than the golf ball, right? Even though you're blowing on them with about the same force. And it all has to do with Newton's second law, that ratio of net force to mass. Now, the last thing that we did was I wanted to see, well, do all objects really accelerate at the same rate? So in this one, what we did was we took a cup, we poked a hole in the bottom, we filled it with water, and then we dropped it, right? So you filled it with water, you held that cup and you dropped it. And you can tell whether those objects, whether the cup and the water accelerate at the same rate based on whether the water goes out the hole at the bottom or out the top, right? You should be able to see objects accelerating at the same rate. So just as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.